Hi students, we are going to discuss about the spherical lenses. Now let us define what is lens. Lens is a optical media bounded by at least one curved surface. See, means a lens is any transparent media. It should be bounded by at least one means it may have two curved surfaces also, and this also becomes a lens, and this also becomes a lens because this transparent material has curved surfaces, and even this also becomes a lens, and this also becomes a lens because these surfaces has at least one curved surface. So these are all lenses, and I call this lens as biconvex lens, and I call this as biconcave lens, and I call this as a plano-convex lens, and I call this as plano-concave lens. And then how can I call this? I call this as concavo-convex lens because the first surface is concave, the second surface is convex. So I can call this as concavo-convex lens, and I call this as convexo-concave lens. Concave lens. But this concavo, convex or convexo-concave, both are same. It differs in its position, that's all. And I call these two lenses as meniscus. Okay. And these plano-convex and concave lens are also considered in certain special cases, but due to its limited scope, we are not dealing with these lenses. We are totally concerned about these lenses, two lenses. One is biconvex and another is biconcave. And henceforth, I call this biconvex as convex lens, or it is also known as converging lens, right? And this biconcave lens as simply concave lens, concave, or I call this lens as diverging lens, right? Now we discuss about only these two lenses in our present discussion, and this is we are not bothered about these lenses, and you come to know in your higher classes about these lenses. Now here convex lens as well as concave lens, both are spherical lenses, means they are bounded by spherical surfaces. Since this convex lens is bounded by two spherical surfaces, then one of the surface becomes a part of a sphere. The other surface also becomes a part of a sphere. That means these two spheres have certain centers, and I call that center as C1 and C2. And even the concave lens is also a part of a sphere. So these two surfaces is a part of a sphere, means they too have the centers of curvatures. So I name it as C1 and C2. If I join these two centers, by a straight line, then I call this straight line as a principal axis. And I do have this principal axis on the concave lens also. Then how can we define the principal axis of a lens? The principal axis of a lens can be defined as a line, a straight line passing through the centers of curvatures of the lenses. And other thing, there is a point inside the lens. I call that point as O. O means optic center or optical center, and that point is one which lies on the principal axis within the lens, such that any rays passing through that point will move undeviated. And such point exists even in the case of concave lens also. See, if I draw any ray passing through that point, will move undeviated. So, then how can we define optic center or optical center? Optical center is a point on the principal axis within the lens, such that any rays passing through that point will move undeviated. When a narrow parallel beam of light get incident on a convex mirror, let's see what happens. So after refraction, all the ray converges to a single point on the principal axis. Yes. And that point lies on the principal axis. And that point where all the rays converges is known as a principal focus. Now let's see what happens when the ray of light parallel to principal axis get incident on concave lens. See, now I am drawing this so that all the rays are parallel to principal axis, and after refraction they diverge. Yes, but actually they don't meet at a single point on the principal axis. But for an observer on the other side, it seems as if the rays has been arrived from somewhere at this point on the principal axis, and that point is known as principal focus of a concave lens. Just see what is the difference between the principal focus on the convex lens and principal focus on the concave lens. In case of convex lens, the principal focus really exists, whereas in case of concave lens, it appears as if the principal focus exists. Means here the principal focus is not real as in case of convex lens. The principal focus is here virtual. So then how can I define the principal focus in case of convex lens and the principal focus in case of concave lens? So in case of convex lens, I define like this. When a ray parallel to principal axis get incident on the lens, after refraction they converges to a single point on the principal axis, and that point is known as principal focus, which is real. Whereas in case of concave lens, when a ray parallel to principal axis get incident on it. After refraction, it appears as if these rays have diverged from a point on the principal axis, and that point is the principal focus of a concave lens, which is imaginary, which is virtual. Now, the distance between the optic center and the principal focus is known as focal length. So, similarly in case of concave lens also, this distance, the distance between principal focus and optic center is known as what? Focal length. Dear students, keep it in mind, there exist two principal focus on either side of the lenses, both convex as well as concave. Here I designated it as F1 and F2 in both the cases. So the plural form of principal focus is called principal foci. So you can pronounce as you wish. Now, in order to obtain images from an object using convex or concave lenses, three rules should be followed. If you get thorough with these three rules, you can easily draw any type of ray diagrams using spherical lenses. See, let's go one by one. The first rule states that when a ray moves parallel to principal axis and get incident on the lens, after refraction it passes through one of the focus. So this is the first rule that you are already know that. And let's see what happens in case of concave lens. See, I am passing a ray parallel to principal axis only in concave lens, and after refraction, here it gets a diverge. So diverge in a direction such a way that it appears as if it got diverged from a fixed point on the principal focus. So this is the first rule for the spherical lenses. Okay, now let's go through the second rule. The second rule states that if I pass a ray through F in case of convex lens, let's see what happens. See, I am passing a ray through F only, and after refraction what happens? It becomes parallel to the principal axis. It moves parallel to the principal axis. Yes. And now, in case of concave lens, what happens? I cannot pass it through principal focus because concave lens doesn't have a real principal focus. So I cannot pass through F1, but I can aim to pass through F2 from this side. See, this is how I am aiming. See, I am passing the light towards this principal focus, which is virtual, and after refraction what happens? It becomes parallel. Means either you pass through F in case of convex lens, or if you aim towards F2 in case of concave lens, after refraction they becomes parallel. So this is the second rule that should be followed. And third rule is very simple. The third rule states that whenever a ray passes through optic center, it moves undeviated. Either in case of convex lens or concave lens. Dear students, get thorough with this rule, then you will be able to draw any type of ray diagrams using the spherical lenses. Dear students, today we are going to learn how to draw ray diagram using the spherical lenses. So to draw ray diagram for spherical lenses, we have to follow strictly the three rules. So at least two rules out of three. And other thing, we are familiar that the lenses, the spherical lenses, has two centers of curvature. I replace this center of curvature with 2f1, as we know that the radius of curvature is half the focal length. That's why here f1 means here 2f1, and I replace this with what, 2f2. Okay. Now I am keeping the object beyond C. Beyond C means beyond 2f1, and I follow the first rule. We state that when a ray parallel to principal axis, after refraction it passes through the principal focus which lies on the other side of the lens. And the rule 3 states that when a ray is passed through optic center, it moves undeviated. Now see what happens, both the refracted ray gets intersected somewhere here. Yes, means the position of the image, lies between f2 and 2f2. And let us discuss what's the nature of the image form. The nature of the image form is, first one, it is real. Why it is real? Because it can be obtained on the screen. Second one, it is inverted. Okay. So regarding the size of this image is smaller compared to the size of the object. So this is diminished because size of the image has been reduced, diminished. Okay. And next, now regarding the position of the image. The position of the image is it lies in between what? Between f and 2f2. f2 and what? 2f2. Okay, these are the four things which we have to know about the object placed beyond what? 2f1. Now let's do one thing. Now we keep the object exactly at 2f1. Now I am following the two rules. The first rule is when a ray is passed parallel to principal axis, after refraction it passes through f2, that you know. And the second ray, when it is passed through f2, what happens? O, it moves undeviated and get intersected at a point here. See the nature of the image. The nature of the image obtained is real only, and the second one is it is inverted. Okay, and third one is regarding the size. What is the size of the image? The size of the image is same as that of the object. That is same size. Okay, same size. Okay, same size image. And fourth thing is the location of the image, where it is lying. It is lying exactly at 2f2. At what? 2f2. And now let's discuss what happens when the object is pushed towards the lens. That is when I keep the object in between 2f1 and f1. Here I am following the same two rules. The first rule, parallel to principal axis, after refraction it moves through f2, and I am following the third rule, that is when the ray passes through where at O, and after refraction what happens? So after refraction, yeah, it gets intersected somewhere here. And now let's discuss what's the nature of the image. The nature of the image is, its first one is real. Okay. Second one is, it is inverted, of course. Inverted. Okay. The third nature of this one is the size of the image has been increased, means the image is enlarged or magnified. Enlarged. Okay. And fourth one is regarding the location or position of the object. The position of the image. The image is lying away from 2f2. So beyond 2f2. Beyond 2f2. Okay. Now I place the object now exactly at f. Let's see what happens. I am following the same two rules, first rule and third rule. Yes, this rays moves, yes, through f, and another ray, yes, it's passing, yes. Now it seems as if these two refracted rays move parallelly. So since they move parallel, they won't meet at near distance, but mathematically they meet somewhere at infinity. Somewhere they meet at infinity means the nature of the image obtained is real only, real, and of course when it is real, it is inverted. Okay. Third one is regarding the size. See, if at all they are meeting at infinity, of course the size of the image is highly enlarged or magnified. So highly enlarged, highly magnified, highly magnified. Okay. And regarding the position or location of the image is, of course, the size is infinitely large, means the distance of the image is also infinitely large. So we shall write at infinity. At infinity. Okay. Infinity is not defined, but from the mathematical point of view, we consider infinity. Means a very, very large distance. Now the final position of the object. Now I am pushing the object still towards the lens, very close to the lens. That is, I am placing the object between F1 and O. Now I am following the same rule, first rule, and after refraction, it passes through F, and another ray, it passes through a optic center O. Okay, what happens? These two refracted ray, of course, they never meet at all. They never meet means, can you imagine that image be formed? So of course, real image cannot be formed, but these two rays appears to have come from somewhere at this point, means yes, these two rays appears to come from this point, and it appears the image has been formed. Image has been formed, and this formation of image is perceived by a human eye because its eye has a live screen called retina. But anyway, you cannot obtain this image on any other physical screen. So let's discuss the nature of the image obtained. The first one is the image is it's not real, means it's a virtual, and second one is, and it is it appears to be erect because the two rays appears to come from this single point which lies above the principal axis, so it's erect. And third one is regarding the size. The size is okay, enlarged or magnified. I should write magnified. Okay. Fourth one is regarding the location. That's not important. According to our diagram, it seems as if it has come from it is lying in between 2f1 and f1. So this is what the nature of images we get at the different positions of the object using what? Convex lens. Now finally we'll see what happens when we place an object in front of a convex lens. See, irrespective of position, the image obtained in the concave lens is same. Whether you keep beyond 2f or at in between 2f or any, irrespective of its position, so you will get the same nature of the image in case of concave lens. Now let's see how we can draw the ray diagram. I am following here the first rule, ray parallel to principal axis, and what happens? So it appears as if the ray has diverged from principal focus, that we already know. The rule 1 in case of concave lens. And another thing is, I am passing a ray, second ray through you. What happens? It moves undeviated. And here, see what is happening. The rays, one is the ray, real ray, and another is the virtual ray. It appears to intersect somewhere here. This is the image that I'll get. So now let's discuss what is the nature of this image. The first nature is, of course, it is virtual, because it's not a real image. It can be perceived by our eye, not by any physical screen. And second one is erect. And third one is regarding the size. The size of the image is smaller than the size of the object, so it's small. Okay, means diminished. Okay. Fourth one regarding the position. The position of the image lies somewhere between what? F and O. So this is the nature of the image in case of concave lens. Hope you understand.